All right, so we are going to review the do now and then just work our way through the notes. We are learning about molecular geometry, but to do that we need to review Lewis dot structures, and there are some exceptions to the rule that you learned before. So today's going to be a pretty decent amount of notes, but this is your last version of notes for this whole chapter. After this, you should be able to pass the focus area, and you should have all the notes you need to pass the exam, which is coming a week and a few days after Thanksgiving break. All right, so let's dive on in. So determine the ionic compound. Remember to cross the charges. So we're going to combine lithium plus oxygen. So lithium is over here. There we go. So lithium has a +1 charge because it has one valence electron, and oxygen takes a -2 charge because it needs two more, 1, 2, to make a full octet. So now we're going to crisscross our charges, so it should be Li2, oxygen 1. All right, let's do Sr, strontium and sulfur. Strontium takes a 1, 2, takes a +2 charge. And sulfur, just like oxygen, 1, 2, takes that -2 charge because it needs 2 electrons to make that full octet. So we're going to crisscross. So we should have Sr2 and S2, which we can condense just to being SRS, because the 2's will cancel each other out. All right, let's do the next one. Potassium has that +1 charge, and phosphorus has 1, 2, 3. It needs 3 electrons, so it takes a -3 charge. I'm going to cross, so we should have potassium 3, phosphorus 1. Good. And then we have magnesium, which takes that +2 charge because it wants to get rid of those 2 electrons. And then oxygen, again, takes that -2 charge. We're going to crisscross our charges, so it should be Mg2 and oxygen 2, which we can condense to being just magnesium, oxygen. Okay. That is the do now. To do this, you need to know how to count valence electrons and determine charge. If you are unable to do this, please come see me, all right? Because the rest of this unit and next chapter is going to be really difficult. So if you are unable to count valence electrons and determine charge, please come see me. I'm here on Wednesdays after school, okay? All right, let's move on. So I would like you to reference this periodic table as we do our work today, okay? I'm not going to be able to show it to you on the screen, so as we work through, if you need to look up at the top of your paper and reference this so you can count valence electrons, okay? All right. So there are a few exceptions to Lewis dot structures. There are exceptions like charges. When a Lewis dot structure is going to have an overall charge, you can either have a positive charge or a negative charge. I'm going to show you how you manage including that charge in your drawing, okay? So let's take NH4 +1. That means this whole compound, NH4, has an overall +1 charge. When we see a positive, it means that we have lost an electron, all right? So how do we set this up? We first line up all of our elements. So we have 1 nitrogen, because there's that little 1 there, and then 4 hydrogens. 1, 2, 3, 4. Now we're going to count the valence electrons. Nitrogen has 5 valence electrons. Hydrogen has 1. We're going to add them up, so 5, 6, 7, 8, 9. All right, and now we've lost an electron, so we're going to subtract 1. So we have 8 electrons total to use. Nitrogen is the one that goes in the center because hydrogen always goes on the outside. I'll repeat that, hydrogen always goes on the outside. So we put our 4 hydrogens surrounding our nitrogen, and then we connect them with 2 electrons each. 1, 2, 3, 4, 5, 6, 7, 8. We've used 8. 8 minus 8 is 0. We don't have any left. So this turns into being N bonded to H, bonded to H. We turn those dots into lines. Bonded to H, bonded to H. Excellent. Okay. Let's look at SO4. So this minus 2 means that we have gained 2 electrons. So just like we did before, we're going to line up our elements. We have 1 sulfur because there's that pretend 1 there, and 4 oxygens. 1, 2 because of that 4. So 1, 2, 3, 4. We count valence electrons. Sulfur has 6 valence electrons, and so do all the oxygens. 6, 6, 6, 6. So it's 1, 2, 3, 4, 5. 6 times 5 is 30. We have gained 2 electrons. We're going to plus the 2. So we have 32 electrons to use. So we're going to find the least electronegative, which is sulfur, because it's 1 row below the oxygen. And then we're going to circle our sulfur with our oxygens. And now we're going to connect them with dots, which are the electrons. So 1, 2, 2 dots per bond. 1, 2, 3, 4, 5, 6, 7, 8. So we've used 8. So we have 24 electrons left. Okay. So now we're just going to box in our oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oxygen has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen's happy. This oxygen has 8. 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen is happy. This oxygen has 8. 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen has fulfilled the octet rule. And this oxygen, 1, 2, 3, 4, 5, 6, 7, 8, has also fulfilled the octet rule. And now let's look at the sulfur. It has 1, 2, 3, 4, 5, 6, 7, 8. So it has also fulfilled the octet rule. So we can just draw our Lewis dot structure with those lines and then putting our dots around the oxygens. So this is our Lewis dot structure. Okay. So typically, a compound will take a charge so it can make a full octet, okay? So if you see a charge, it's because the normal valence electrons do not give it a full octet. So it has to lose or gain electrons to make that happen. All right, so those are charges, okay? That's a certain specific type of Lewis dot structure. Now we're going to dive into some exceptions to Lewis dot structures. Some exceptions are an incomplete octet, so that means one of the elements won't have a full octet, so won't have 8 valence electrons. Okay, and an expanded octet means it'll probably have more than 8 valence electrons, okay? So let's look at these examples. Same thing, we're going to start with BCl3, so boron trichloride. We're going to list out our elements. So we have 1 boron, because there's that pretend 1 there, and then the 3 Cl, so 1, 2, 3 chlorines. We're going to count the valence electrons. Boron has 3 valence electrons. Each chlorine has 7. 7 times 3 is 21. 21 plus 3 is 24, so that's 24 total electrons. We put the least electronegative in the center, which is going to be boron because it's farther to the left. And then we're going to circle our boron with our 3 chlorines. Now we're going to connect each element to the boron using our dots. So we have 1, 2 electrons, 3, 4 electrons, 5, 6 electrons. We've used 6 electrons, which leaves us with 18 electrons to put back into our structure. So we're going to start putting our dots around our chlorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So each chlorine has 8, but the boron only has 6. And that's fine because this is a complete octet, so boron will not have 8 valence electrons. So if we redraw this, boron is bonded to chlorine, and each chlorine is going to have the dots around it, the electrons around it. Okay. So that's an incomplete octet. Boron only has 6 valence electrons, not 8. For our expanded octet, same thing. We're going to list out our elements. So we have 1 sulfur and 6 fluorines. 1, 2, 3, 4, 5, 6. Okay. Sulfur has 6 valence electrons and all the fluorines have 7. 7, 7, 7, 7, 7, 7, which gives us a total of 48 electrons. We're going to pick the least electronegative, which is sulfur, because it's a row below fluorine and it's also further to the left. So sulfur is our least electronegative, so it will go in the center. And we're going to surround our sulfur with our 6 fluorines. So we're going to put a fluorine up top and a fluorine on the bottom, that's 2. A fluorine to the side, that's 3, 4, 5, 6. All right, and now we're going to connect with our bonding electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used 12 electrons, which leaves us with 36. So just right now, before I put any more electrons into the structure, sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons connected to it. Not 8, 12. So it has expanded into an extra energy level to take on those extra electrons. And this is why it's an expanded octet, because it has 12 electrons instead of 8. Now I'm going to put in our 36. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So if I was just to redraw this down here, it's sulfur bonded to the 6 fluorines with the dots electrons surrounding those fluorines. Okay, so this is the answer. Okay, and again, sulfur has 12 valence electrons. instead of that 8. So we have expanded its octet. So these are the exceptions, okay, to the octet rule. Now we're going to dive on into molecular geometry, okay, and practice more Lewis dot structures. Okay, let's keep going. So molecular geometry, what is it exactly? It is the 3D shape a molecule takes. Okay. And these 3D shapes affect certain properties. Like the chemical and physical properties, okay? All right, so it's going to affect the melting point. It's going to affect the boiling point of the compound. The solubility of the compound. And the type of chemical reaction. Okay. Also, each of these 3D shapes are going to either be polar or nonpolar. Okay. So let's go learn about these shapes. So we're going to look at the compound, draw its structure. I'm going to tell you what the name of its shape is, and then I'll tell you if it's polar or nonpolar. Okay? So we have CO2. So we're going to list out. We have carbon, 2 oxygens. Carbon has 4 valence electrons. Oxygen has 6. That's a total of 16. We're going to put our least electronegative atom in the center, so that's carbon. We're going to connect our carbon to our 2 surrounding oxygens, and then we're going to place our electrons. So we've used 4, 1, 2, 3, 4. That gives us 12 left, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 2 outside oxygens do not have enough valence electrons, so we're going to move. Oh no, not those, sorry. We're going to move the 2 connecting electrons of carbon to the outside. So we're going to have oxygen with 2 and then carbon with those centers. So now carbon has 8 and each oxygen has 8. We're going to redraw this. So those 4 electrons become a double bond. And now we're going to look at the polarity. Okay, so this is oxygen takes a 3.5 electronegativity value and carbon takes a 2.6, which is a difference of a 0.9. So between oxygen and carbon, it's a polar interaction. However, carbon is more positive, oxygen is more negative, and carbon is more positive and oxygen is more negative. So those oxygens are pulling on those carbons with equal force. So the overall polarity is non-polar. Okay? Because the oxygen pulls on carbon with the same force as the other oxygen pulls on carbon. All right, it's 0.9 pulling in one direction and 0.9 pulling in the other direction. Same force, they cancel each other out. The molecular geometry is called linear. This is in a straight line. So when you see this shape, this is the linear shape. Okay? Good, let's move on. Our next compound is boron trifluoride. So we have 1 boron, 3 fluorines. Boron has 3 valence electrons, fluorine has 7. That's a total of 24 electrons. Boron is going to go into the center, okay? Because it is the least electronegative. Our fluorines are going to circle our boron. We're going to connect them with our connecting electrons. 1, 2, 3, 4, 5, 6. So we've used 6 so far. That leaves us with 18 to put into our structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So our structure looks like this. Boron bonded to the 3 fluorines with those surrounding valence electrons. Okay. Now, the electronegativity between boron and fluorine is 2. So our fluorine is 4 minus 2, which gives you a difference of 2. Okay. And so fluorine is more electronegative. Actually, I'm going to move this. So fluorine is more electronegative. Fluorine is more electronegative. So those 2 fluorines are going to cancel each other out. However, this fluorine does not get canceled out, which makes this shape polar. Okay? And so this is a difference of 4 minus 2, which equals 2. So we have the forces of the 2's pulling on that boron right and left, and then that 2 pulling down, which does not get canceled, which makes the shape polar. This shape is called trigonal planar. Again, these values in the red are found on a chart. Okay, I will give them to you. All right, next shape. Okay, this is methane, but don't worry about that. It's 1 carbon and 4 hydrogens. So we have 4 valence electrons for carbon, 1 valence electron for each oxygen. That's a total of 8 valence electrons. The carbon goes in the center. The hydrogens always go on the outside, surrounding the element they're bonded to, which right now is carbon. We're going to connect my elements with those bonding electrons. We've used 8 of them. We have no more left, so the shape is carbon bonded to the 4 hydrogens. Now, carbon takes a 2.5 charge. And hydrogen takes a 2.1, which gives you a difference of 0.4. Carbon is the more electronegative. So this 0.4 will cancel this 0.4. This 0.4 is going to cancel this 0.4. So this shape is non-polar. polar. And 0.4 is also nonpolar. Good. And this shape is called tetrahedral. Tetrahedral. Okay. We have 2 more left, and that's it. All right, our next one is ammonia. So we have 1 N, 3 hydrogens. We count those valence electrons. N has 5, hydrogen each has 1. That's a total of 8. Hydrogens are always on the outside. They're going to surround the nitrogen. We're going to connect them with our 2 connecting dots. For each, that's 1, 2, 3, 4, 5, 6, so minus 6. 8 minus 6 is 2. That leaves us with the 2 on top of the nitrogen. So our shape looks like this, with those 2 dots up there. Those 2 dots are important. Hydrogen, well, actually let's do nitrogen first. Nitrogen minus the hydrogen. Nitrogen takes a 3 electronegativity value. Hydrogen takes 2.1. That gives a difference of 0.9, which is polar. Nitrogen is more electronegative. So let's put this, it'll be easier if you see it down here. So it's more electronegative, more electronegative, more electronegative. So the hydrogens are going to cancel each other out on either side of the nitrogen. And then this hydrogen is going to try and cancel out this lone pair, but it really won't be able to, so this is going to be polar. The overall polarity of this compound is polar, and this shape is called trigonal pyramidal. Good. Okay. And last one. Okay. So we have our 2 hydrogens and our 1 oxygen. Hydrogen each has 1 valence electron, oxygen has 6, that leaves us with 8. We put our oxygen in the center, we surround it with our hydrogens, we connect them with our connecting electrons. We've used 4, so we have 4 left, then we put them 1, 2, 3, 4. So our shape should look like this. And we're actually going to keep our electrons together up top. Oxygen electronegativity value is 3.8 minus hydrogen's electronegativity value, which is 2.1, which gives us a value of 1.7, so this is polar. Oxygen being more electronegative is a negative value. Since these are at an angle, they don't cancel. Oh gosh, I don't know what I'm spelling. There we go, cancel, sorry guys. Okay, so this is going to be polar, and these electrons are going to pull and be negative upwards. And this shape is called bent. Okay, awesome. Make sure that you know the shape, its name, and its polarity. You must memorize these. I will quiz you on them on the test many times. There might be a pop quiz after Thanksgiving, just a heads up. Okay, let's go do some practice problems and really start to use this material and start to memorize it. I know this was a long video, but you guys did really great. Keep up the good work.